Yep.
So our speaker today is Nathan Brownlowe from the University of Sydney, and his title, as you can see there, is Self-Similar Quantum Groups. Please, Nathan, go ahead.
All right, thanks a lot. And thanks to those in the audience who've come along and to watch this seminar. And thanks for the invitation to speak at this seminar series. I'm off to a conference in Edinburgh in a couple of weeks, and it'll be the first conference I've attended since 2019. And I haven't exactly given a lot of Zoom seminars in the meantime, so it feels like it's been a long time since I've done this type of thing. But I'm looking forward to this and looking forward to actually getting to a conference soon. So today I'm going to talk about joint work with a colleague, Dave Robertson, who's here in Australia, in New South Wales, at the University of New England. And I actually spoke to him today, but it's 11 p.m. here, and he politely told me that he would be busy and would miss my talk. And I said, no, that's fine. I'm going to talk about a fairly simple idea, I think, but and I'll talk about the question on the next slide. But this was some years in the making. We were, in the past, Dave and I, with others, had worked on Zappashev products and C-star algebras. And at some stage, we started thinking about Zappashev products of quantum groups. And we got some things working, but not really, and we couldn't really get it off the ground. The Zappashev products had been related to self-similar groups. And so eventually, we wound up with the question of whether it makes sense to talk about self-similarity for quantum groups. Let's see. So our motivating question for this this project was this simple one, and a lot of my talk will be some background on these topics. Is there a sensible notion of self-similarity for quantum groups? And I think we have one. And we wrote this up, put it on an archive in February. So this talk is based on that work. I plan to go through and sort of give a bit of a recap on self-similarity of groups. And also I'll start with some background on compact quantum groups. They're the types of quantum groups I'm talking about. So apologies if you know all about these two topics, but hopefully maybe there's some in the audience who at least don't know much about one of these two. Okay, so for the first part of my talk, my goal is to present the definition of a compact quantum group. If you just stare at the definition from scratch without knowing anything about it, I mean, it's quite a strange thing, but I think you can motivate it quite nicely looking at the classical setting. So, all right, so I'm going to start with the usual thing. I don't know whether this should be forbidden or whether it should be mandatory. But I'm sure most of your talks here in this seminar start along these lines. So we'll start with Gelfand duality, this correspondence between, in this case, I'm in the unital setting, spaces and functions. So we have this equivalence between compact Hausdorff spaces X and commutative C-star algebras, right? Via looking at the continuous functions on X. And we can go back via looking at the spectrum of a commutative C-star algebra. So thanks to Gelfand, this is very well understood. But we also have plenty of very natural and basic examples of non-commutative C-star algebras. So if we want to study non-commutative C-star algebras, then maybe because inspired by that correspondence, doing so will capture some sort of notion of, a non-commutative, or let's say a quantum space on the other side. And if you throw some extra structure on the right, on the non-commutative C-star algebras, then you'll get different types of these quantum spaces. And quantum groups fit into this framework. And I'm going to tell you, what structure you can put on with the non-commutative C-star algebra to get what's called a compact quantum group. Okay, so as I said, I want to inspire this definition by looking at the classical setting, so like the commutative setting. So suppose G is a compact Hausdorff group with multiplication M. Then associativity of M can be expressed. This is not how we usually write associativity, of course, of multiplication, but we can express associativity with this commutative diagram. Right, so if we start with 3 copies of G up the top left, and we can multiply, first and second component or second and third, and then multiply again, we end up with G. So associativity is saying that this diagram commutes. So I want to take the dual of this diagram, right? So I want to look at functions now. And this is a contravariant thing. So when I take the functions, our maps go the other way. So my multiplication went from 2 copies of G to 1. The dual of this is what we call co-multiplication, delta, going from C of G to C of 2 copies of G, which is also the tensor product of C, G with itself. And so delta of F is just F composed with the multiplication. So coming from the fact that I have this group G, I have this associative multiplication, I can dualize this and I get all of this for free. I mean, I need to prove that it works, but we get this commuting diagram for co-multiplication. So I want to keep the arrows going from top left to bottom right. So I've had to flip around the position of the object. So now I'm going from 1 copy of C of G on the top left down to 3 copies of C of G. But yeah, we get a picture inspired coming from multiplication. We also get something else that's a bit technical and not so important for us. We get that we have these 2 dense subalgebras sitting inside C of G tensor itself, or the functions on 2 copies of G. So yeah, you prove this with Stone-Weierstrass, and you need the fact that G is a group here, not just a space, but G is a group. That helps you show that you can separate points in your Stone-Weierstrass argument. So you get this thing at the bottom. Okay, so this is what you get out of C of some group, compact group. And then that, I think, leads naturally to the definition of a compact quantum group. So this is from Woronovich in '87. Well, it's definitely due to Woronovich, but he wrote a series of papers on compact matrix quantum groups and then later compact quantum groups. But yeah, Woronovich came up with this notion of what we call a compact quantum group. So a unital C-star algebra replacing C of G, and we want some co-multiplication. And now we have to insist that we have this commuting diagram and that we have these 2 dense subalgebras at the bottom. These linear spans are dense in A tensor A. Okay, so yeah, if like I said, maybe some in the audience haven't seen much of quantum groups before. They're not just groups, they're sort of much more complicated objects. I'm going to go through one example, but it's a huge theory, compact quantum groups, and the generalizations to locally compact quantum groups, discrete quantum groups, and there's a whole purely algebraic side to quantum groups. So it's a huge field. Lots of interesting examples. I'm just going to go through one that will be sort of relevant to the setup of the self-similar.
May I ask a little question? You do not require the existence of an antipode. No, so Woronovich showed that all this Hopf algebra structure is sitting there in the background. So if you have this Hopf algebra, with the antipode and the co-inverse, co-unit, co-inverse, the antipode,
then you can complete and get one of these guys. Also, starting from this, you can get a dense subalgebra that has this top algebra structure.
Okay, thanks.
Okay, so yeah, so that's the definition of compact quantum group. What about an example? So I'm going to look at a quantum symmetric group or quantum permutation group. So as we know, Sn, I'm going to call the group of n by n permutation matrices. All right, so 0, 1 matrices with a single one in every row and column. I want to look at a special class of functions to inspire the definition of the quantum permutation group. So for each I and j between 1 and n, I want to just let Fij take in a permutation matrix and spit out the Ij entry, right? So this is going to be 0 or 1. Okay, so these functions will generate the continuous functions on Sn, and they satisfy these relations. So they're clearly projections, just having value 0 or 1. And because we're picking out entries of a permutation matrix, if we fix one of the indices and let the other one run, then these matrices have a single one. So we're going to get the identity from these two sums. All right, so these functions satisfy this. I also want to think about what the co-multiplication does to these functions. Right, so this is a group. We get a co-multiplication on the functions. Right, so delta Fij. We now input a pair of permutations. As we know, this is the function composed with multiplication. So Fij at the product sigma tau. And so we're picking out the Ij entry. And as my first year linear algebra students can tell you, this is the sum of k equals 1 to n of that product. But this is exactly the sum of Fik tensor k Fkj, where you're letting k run at that pair sigma tau. Right? So delta of one of these Fijs spits out this sum of tensors. Okay, so these functions and these relations and what co-multiplication does, a little bit like inspiring the definition of the compact quantum group. This is meant to inspire what we now know as the quantum permutation group. So this is from Wang back in '98. So he defined, and there's different notation for this, but I'll let ASN be the C-star algebra generated by elements Aij, Ij run from 1 to n, satisfying exactly these relations. So we've taken the functions on Sn and just lost commutativity, right? So these are projections. You have these sums to 1, and he proved that there is a co-multiplication delta satisfying the same formula that the co-multiplication on C of Sn satisfied, and he proved that this pair is a compact quantum group. And we call this the quantum permutation group of the set 1 to n, or of n points. So Wang's work was inspired by a question of Kohn back, obviously before '98, that he was asking whether there was quantum symmetry of a finite set of points. And so this was Wang's answer to that question. But it's interesting that we actually need at least 4 points to get any quantum phenomena. So it's not too hard to see, although I'm not giving all the details. So Wang showed that this C-star algebra is non-commutative and infinite dimensional if and only if n's 4, at least 4, sorry. So the relations on Aij are precisely set up to put them in a matrix, and people call a magic matrix. So this is one that has projections for entries and the rows and columns sum to 1. So if we do this, in n equals 1 case, we just have the 1-by-1 identity. So we get the complex numbers. Okay, boring. N equals 2. If you want these relations, then the 1, 1 entry P, some projection, it totally dictates everything else in your matrix. So AS2 is some C-star algebra generated by a projection C2. N equals 3 is more complicated, but you can show that AS3 is a commutative C-star algebra. And so when you get to N equals 4, you have this 4x4 matrix, you have room to do things. So if you take P and Q non-commutating projections, this is the standard way to sort of argue this out, then you have room to sort of fit the P's in that upper block and the Q's in the bottom. They're not interacting, the P's and Q's, but this is clearly one of these magic matrices, right? Rows and columns sum to 1, or projections. And this is the C-star algebra generated by P and Q is non-commutative and infinite dimensional, and so is AS4 and beyond. Okay, so you need at least 4 points to get quantum symmetries. But yeah, this is an example of a compact quantum group. And one of many in the same sort of class where you look at the functions on the group and you lose commutativity, right? Okay. All right, so that's my recap on compact quantum groups. Now I want to start talking about classic self-similarity, and then I'll combine the two and eventually define what we call a self-similar compact quantum group. Okay, so self-similarity. So throughout the rest of the talk, I want to let X be a finite non-empty set, and it better have at least 2 elements for it to be interesting. And X star is the associated infinite homogeneous rooted tree, right? So I've got a picture in a couple of slides, but you have a root on the top, and then you have, the size of X number of edges coming out at each level, right? And it goes on forever. So I want to look, the group in question I want to look at is the automorphisms, right? This in general has a big automorphism group, this infinite rooted tree. If you give this the compact open topology, or it's known as the permutation topology, this group is a compact, totally disconnected Hausdorff group. And okay, I've written down a sub-basis of compact open subsets. If you give me 2 words, so I called X star the tree, but so there's sort of like all the vertices in the tree, they correspond naturally to words in X, right? So if you give me 2 vertices in the tree or words, then I can look at all the group elements that send, that should be V to U, just the way it won't really make a difference in this talk, but yeah, usually I define G, U, V to be all the little G's that send V to U. They need to be the same length if you're going to have things in here, otherwise you get empty, right? Because we're preserving the levels of the tree. Okay, so if I take my favorite word W and an automorphism G, then if I look at everything under W, and I have this basically the same slide in pictures on the next one. If I look at everything under W, so W plus something, right, concatenate it with some extra word, then this is just the same tree as G of W X star, and it's the same as the whole tree to begin with, right? So WX star being the same as G of WX star means that from G, we get an automorphism G restricted to W. That's how I use this notation, call it G restricted to W. This is now an automorphism in X star uniquely determined by the following equation. And so G is acting on words longer than W, and G restricted to W is just telling you what it does to the word beyond W. Okay, so G does something to W, and then it's got to do something to the rest, and that's what this restriction is doing. Yeah, we call G restricted to W the restriction of G by W. And so here's the definition, one way to describe it, of a self-similar group. So take a subgroup of the automorphisms on this tree, and we capital G, and we call it self-similar if it's closed under restrictions, right? So This has to happen for all W, for all words W. If you take an automorphism in G and restrict it to any W, you've got to land back in G. So I'm going to look at the functions, right, on some topological group. This is how I started, inspiring the compact quantum groups. And then we're going to quantize, right, and get a notion of self-similarity. So really what's going on here in our definition of self-similar quantum groups is we're really quantizing the idea of a closed self-similar group. But thankfully, this map, like fix a W, and this works for any W, this map that just takes an automorphism and restricts it to another automorphism, this is continuous. And so the closure of any self-similar group sitting inside the automorphisms is again self-similar. Okay, so there you go. There's a bit of a picture for what it's worth. So imagine these trees are infinite. This is like a binary rooted tree. I've got some map from it to itself, some G, little g, right? I've picked this in some subgroup capital G. And the idea is if I want capital G to be self-similar, then, right, I've got some word W here. If I look under W, I've got the blue tree. Let's say little g maps it across to the red tree. Then if I just focus on the automorphism sending the blue to the red, which again is a map from X star to X star, then as long as I always land back inside this G, then I can call G self-similar. Okay, so that's the picture behind self-similarity. And some examples. So the canonical first example you see is the binary odometer. So for both of these examples, let X have have size 2, so let it be 0 and 1. So let G be this particular automorphism. So G of 0W, so a word starting with 0, just takes that 0 and turns it to a 1. And G of 1W, so if your word starts with 1, then you change the 1 to a 0, but then you do G to the rest, right? So this is an example of an automaton. People use these all the time to generate these self-similar groups. And I'll have another example in a second. So yeah, if you think through those two formulas, then you realize that this is binary addition, really, right? So the group generated by this single automorphism, which is clearly a copy of the integers because we've just got a single generator. It's not the group itself, it's really how it's acting in the tree. We call this the binary odometer. And if you close it up and go through the fiddly details, then the closure is the two-adic integers sitting inside the automorphisms of this binary rooted tree. Okay, so another example, and either you've seen it and yep, same old story, or you haven't, and none of what's on the screen really matters. But you can get a very famous group, and there are many famous groups coming from this sort of procedure. But you can get this particular one out of 4 automorphisms on a binary rooted tree. So A, B, C, D are my automorphisms. Again, just like I told you what the binary odometer generator did, I'm telling you here what A and B, C, and D do to all the words. So for instance, A, we see just takes a 0 at the start of a word, changes it to a 1, leaves it alone, and does the opposite, right? If you start with 1, changes it to a 0, leaves it alone. Whereas the rest of them do something a bit more complicated. So anyway, you get these 4 automorphisms. You can generate a subgroup of the automorphisms of X star, and this is called Grigorchuk's group, or the Grigorchuk group. So this is a very famous group that came about in 1980 that solved a bunch of problems, or was a counterexample, if you like. So amenable but not elementary amenable, and finitely generated but with intermediate growth. So a very famous group, the first group to have a lot of important properties. Yeah, and the theory of self-similarity, I think that's it. I've got another general class of examples, but I'll say it now. The theory of self-similarity is still very much flourishing, and it's a really big field within like geometric group theory and group theory itself. Yeah, so just a class of examples, because this is the one that this class is what we do with the quantum things. So finite, was that a question?
No. Yeah, the definition of this x to the d reminds me of Katsura's algebras. Does it have is the linear relation?
Katsura's
because you take a remainder, I mean, you take it's just the selection of the integers on a finite set of n elements, which is defined by taking you act by sending an element to you fix a parameter and you send an element to, you translate it by the parameter, you add something, this fixed parameter, and then what you call the G restricted to W is given by the quotient with respect to. So there is a remainder and a quotient. But
right. But I don't think it's related. I think it just looks related. So this x to the d, or square bracket d, is the finite subtree containing the root up to some level. So level d, I guess. And RD, and I call this RD, this function, is really restriction, but actual function restriction, not restricting to words as in I defined for self-similarity, but actually take an automorphism on the whole tree and just restrict it to the first d levels of your tree. So this G restricted is different to the other notation. This is actual function restriction, and I won't use it again. I'll use RD. Yeah. So yeah, you have that set up. Sorry. And so now you take a subgroup of the automorphisms of this finite tree up to level D. And then you define this set GP. So you look at all the automorphisms in the whole tree where if you first restrict to a W, as in the restriction we've been dealing with, and then apply RD, all right, that just means view what happens on the first D levels, then you land back in P. Okay, so you start with this smaller subgroup on the D levels, look at all the things that restrict down, all the things on the big tree that restrict down to being something in P, and this has to happen for all W. Okay, so there's some gibberish in this dot point, but I'm just trying to show that this is an actual subgroup. So it's closed under multiplication and inverses. So if you take two elements, G and H, and a W, then we have formulas for these. So how is the product restrict to a W, and how's the inverse restrict? It's not meant to be at all obvious if you haven't seen these formulas, but we have formulas for them. And the point is that if you stare at those formulas, this tells you because G and H started in GP, that these restrictions land back in P. And so the product GH is in GP, and the inverse of something in GP is back in GP. So this is a subgroup. And I mean, Gregorchuk came up with these groups, and these are self-similar. They're built to be self-similar. If you look at GP, you're forcing all these restrictions to land back in P. Well, of course, if you take something like that and restrict it first, then you're going to be fine. So it's self-similar. I haven't written it, but Gregorchuk's group can be phrased using this, this language. I don't know offhand how you write that down. Okay, so there are some more examples of self-similar groups, and there's whole big classes of examples that I'm not going through. Okay, so I'm trying to head towards now self-similar quantum groups. So just like I picked out functions on the special functions on the continuous functions on the symmetric group, I want to pick out special class of functions in the set of continuous functions on the automorphisms of X star. So if I have two words U and V of the same length, I want to look at FUV to be an indicator function on these GUV sets. And here I've written it how I intended, or the automorphisms that take V to U. So these are my special class of functions. Each FUV is a projection, it's just an indicator function, and they satisfy the following. So if you fix an X, right, and sum over all the FUX VYs, where you let Y vary, then you're just going to capture FUV, right? Because if G takes V to U, then it's going to take V something to UX, right? There's going to be one Y that hits it, and only one. And you get a similar story for the other sum. So these functions satisfy this. And then what about co-multiplication, right? So we've got a group, the automorphisms. We can dualize multiplication. We get a co-multiplication on the functions. So delta FUV of GH is FUV of the product as usual. And so this is 1 if the product of V is U and 0 otherwise. And so this is composition. So we really need, if the composition is sending V to U, we need some step in the middle, W, say, where H takes V to W and then G takes W to U, right? So you can think through and convince yourself that this corresponds to the sum over W of the same words of the same length of these tensors at a GH. A very similar formula to the one we were seeing for the symmetric group. Okay, so that was the commutative, functions on the classical automorphism group. We want to move toward quantum automorphisms, right? And then our replacement for self-similar subgroups of the automorphisms will be quantum subgroups of this quantum automorphism group. Okay, so let AX be the universal C-star algebra generated by AUVs, right? Again, inspired by these FUV functions. We want A empty to the identity, and then projections and the same relations for the sums, right? So we've lost commutativity. We want everything else that those FUVs gave us. And we showed, and I've put some other names there, which I'll mention in a second, that the C-star algebra AX is a compact quantum group, and it has a co-multiplication delta, satisfying, the same sort of formulas we've been seeing, right? And so we call, with justification, this C-star algebra and this co-multiplication, the quantum automorphism group of the tree. Yeah, I put Rollier-Weiss there as well. In the final stages of Dave and I sort of putting all this together, we only just realized that they had a paper towards the end of last year, a preprint, where they looked at something much more general. They looked at actions of locally compact quantum groups on connected locally finite graphs, I think. And actually, this setup in the compact setting, and if you take a rooted tree, you can have it fit their setup and get this algebra and this co-multiplication. Okay, so that's our replacement for the functions on the automorphisms. And now we need to work towards self-similarity, right? Well, we need an idea of restrictions, right? Self-similarity was all about being closed under these restrictions. So I want to be, again, inspired by the function setting, what happens to restrictions on the functions on the automorphisms? So we've got this map that fixes a W, and we've got a map that sends an automorphism G to the restriction. Dualize this, right? And so we get a homomorphism from the functions on the automorphisms to itself, given by the same old formula. I'm calling this homomorphism rho. Rho W of F at G is F of, the previous map we're dualing, so dualizing G restricted to W. Okay, so what does this dual of restriction do to one of these FUVs that I've highlighted, right? That I've sort of claimed are important. So rho W FUV of G is FUV of G restricted to W. Definition of FUV, this is 1 if G restricted to W sends V to U and 0 otherwise. But if the restriction to W sends V to U, this will happen precisely when G sends WV to something U, where something is of the right length, right? And if there is such a thing, there'll be one such thing. So if we sum over all y's of the same length of W, of these functions FYU, WV, we'll pick up that previous term. So now we get a formula for this dualized notion of restriction, the classical self-similar restriction to the functions, right? And again, inspired by that, you can prove that this quantum automorphism group of the tree, AX, right, this big C-star algebra, has these homomorphisms for each W, have these homomorphisms rho W that send an AUV to this sum. And we call rho W restriction by W. For what it's worth, I don't know if it's worth much, but if you like thinking in terms of pictures, an example of sort of what's going on is, let's take X to have 3 elements. And so I've got some sort of unit square that I'm splitting up into 3 by 3 in the first instance, right? So and each of these little boxes corresponds to one of these projections. So this would be A00, A01, A02. I should label these. But the black one here on the left is my A12. And then I'm doing row 1. So my W is just the letter 1. And so using this formula, I stick a 1 at the beginning of the second index, and I sum over 0, 1, 1, 1, 2, 1. So this single black box is getting sent to the sum of these smaller projections. Right, so this is index, this right-hand side thing is split up into words of length 2. But there are 9 such words, so this is a 9 by 9 grid, right? Anyway, so that's restriction. We have a notion of restriction on our quantum automorphism group. And so now it's natural to get at self-similarity. So just a standard definition in quantum group world. The idea is subgroups for quantum groups correspond to quotients, right? So if you start with the compact quantum group A delta, a quantum subgroup is a quotient. But you've got to be careful about what ideal you're quotienting by. So you need the ideal to play nicely with co-multiplication. So as long as delta of I is contained in the kernel of Q tensor Q, you can you have yourself another compact quantum group based on the quotient A mod I. Okay, but they called subgroups. And so here's the definition of self-similarity. So a quantum subgroup A of this quantum automorphism group of the tree is called self-similar. If for each X and X, I'm describing this in terms of the letters, but you can show that it's equivalent to doing this for words W. If the restriction rho X factors through the quotient map. In other words, there's a homomorphism from A to A that makes this diagram commute. So rho X on top here is this restriction map. Yeah, so self-similar compact quantum groups are subgroups of this quantum subgroups of this AX that satisfy this condition that sort of play nicely with this restriction map. Yeah, so these finitely constrained examples work nicely in this setup. So again, let D be some integer bigger than or equal to 1. Think of this as being just a finite part of the rooted tree, including the root. Let AD be the the subalgebra of AX generated by the AUVs, where you only go up to length D. And you can see that you can convince yourself that co-multiplication restricts down nicely. You get what's called this AD is a quotient quantum group. It's a subalgebra. Okay, so you got this AD. Take a quantum subgroup of AD. I'm going to call that P. All right, so remember, quantum subgroups are quotients. So we've got some quotient. P is like AD mod I for some I. Okay, so take that I, like the kernel of the quotient map, hit it with all row W's, right? So just hit it with the restriction map and generate an ideal in AX. I'm calling this J, right? So you start with an ideal of AD, you hit it with all the restrictions you can, and generate a C-star algebra, an ideal in the bigger C-star algebra AX in the quantum automorphisms of the tree. And then AX mod this big ideal is the analog of these finitely constrained examples, and each one of these is a self-similar quantum group. And then my almost final slide, I have some just some future work on the next slide. But it is well known, whatever that means. If you know it, you know it. If you don't, you don't. Classically, that the automorphisms on, say, the tree up to length D+1 is the wreath product of the automorphisms of the tree up to length D and the symmetric group on X, right? And then it follows from that, or maybe most people know the second dot point, that the automorphisms on this binary, not binary, it's this rooted tree, is this iterated wreath product of the symmetric group on X, right? So it just keeps going. And more generally, if you take a subgroup of the symmetric group, and the symmetric group here is the automorphisms on X of level 1, right? Then the finitely constrained self-similar group GP that I went through a few slides ago before we got into the quantum self-similarity is also the infinitely iterated wreath product of P. Right, so this all happens classically, and so we wanted to check whether this happens with self-similarity, and it does. So okay, I've got a phi. I've been calling all of these deltas, but anyway, A phi is the co-multiplication. A phi is a compact quantum group, and you take a quantum subgroup P of A1. Notice A1 is just the symmetric group on whatever the size of X is, right? So it really is that example from before of a quantum version of symmetric group. Then you can define a free wreath product, right, of A by this quantum subgroup of quantum symmetric group, and you get back a compact quantum group out of this construction. And then if your A is the AP, right, these finitely constrained examples, then you're just picking back up the wreath product of AP and P, right? So this is the analog of, if you keep doing this, right, you get this AP is this, well, if you like, I could rephrase this GP business as GP is the wreath product of itself and P. And this is the analog of that. And I've got Bichon's name up there because Bichon was the first person to talk about these free wreath products. And he took a free wreath product of a compact quantum group by symmetric group, quantum symmetric. And the proof that we have is you know, totally along the same lines. his, and in fact, he has a remark in his paper that you could do the same thing for not just using the whole quantum symmetric group, but a quantum subgroup of it. So that first dot point is sort of claimed in a remark in Bichon's paper. Okay, so that's basically it. That's what we did in the preprint in February. Just a couple of things. So examples, like more examples, right? Like, I mean, my idea is that self-similarity is really important in group theory. It's, you know, it's been around for a long time now, right? Gregorchuk made his group in 1980, but it's done lots of great things and produced lots of excellent examples. And, you know, I have no idea how this self-similarity will go down in quantum group world, but I hope that it could provide some interesting examples, an interesting theory. I'm certainly not going to be approaching anything on the level of the classical self-similar groups, but I'm sort of optimistic that it'll produce a nice theory. So we need more examples. Barnecker and Bichon have a paper where they classify all the quantum subgroups of AS4, right? This first symmetric group that's actually quantum symmetric group that's actually non-commutative. So they have this long list of strange looking quantum subgroups. And so this construction spits out, like the AP, the finitely constrained one, spits out self-similar quantum groups for us. So what are they and what can you say about them, right? The next two are sort of vague, and I forgot to remind myself of the definition of the third dot point. But anyway, we playing around with examples, we noticed that if you, I think it's called the Proofer group. Maybe someone can correct me, but basically the 2n roots of unity as you let n vary. So its dual is the two-adic integers. So the Proofer group, C star algebra, C star G, its commutative group, it's the functions on the two adics, which is the functions on the closure of the binary odometer. So this is a C star G is self-similar in our sense, the group C star algebra. But that's a commutative example. Are there any non-commutative examples of G, discrete groups G, whose group C star algebra, which you can view as a compact quantum group? I didn't talk about it as an example, but you can. So we want self-similarity of the C star algebra. And does that mean anything for G? Are they interesting? I don't know. And self-replicating examples, I had a conversation with George Willis, who lives down here. And he's big on these classical self-replicating self-similar groups. And I think we can write down a sensible notion for self-replicating for quantum self-similar groups. But yeah, I've forgotten what self-replicating means offhand. Self-similar discrete quantum groups. So I noticed Mike, I don't know if he's still around, but I noticed Mike Whitaker in the audience. Yep. So with Mike and Christian Voigt both in Glasgow, Dave and I have been talking to those guys and looking at a couple of things, but one of which is discrete quantum groups. I don't have a full appreciation of what discrete quantum groups are, but given self-similarity, and how they're sort of built from automata, like classically, maybe discrete quantum groups is a more natural home than compact quantum groups, right? Or maybe there's a nice relationship between the two. I don't know. But especially thanks to sort of Christian's work, like we might have something you could call a quantum Gregorchuk group, and it's one of these discrete things. So it's got generators that mimic, the Gregorchuk generators. And what have I said? Oh, yeah. If there's a notion,
may I ask a question?
Yeah, sure.
Is discrete quantum groups like a dual of compact quantum groups?
The short answer is I don't know. I'm not firm enough. I have heard that sort of language. Maybe someone in the audience knows more than me. Well, they're bound to, but I'm too scared to answer yes to that one. People are saying in the chat. What are they saying? Yes.
Okay, thank you.
So I'd heard that, but yeah, Discrete quantum groups are still a mystery to me, even though they sound like they should be easier. And maybe they are, I just haven't looked at them properly yet. Yeah, anyway, my last dot point was on growth rate. So, Dvorak's group, partly what made it famous was it had intermediate growth, finitely generated intermediate growth. And so there is a notion of growth rate for discrete quantum groups. There doesn't seem to be a lot out there, I don't think. Maybe I'm wrong, but that maybe this is maybe how self-similarity can be interesting in the world of quantum groups. So, all right, yeah, just various references of some things I actually sort of mentioned and just this standard papers in these topics. But yeah, thanks a lot for listening.
Thank you very much, Nathan, for a very interesting talk. I see, what do I see in the chat? Let me see if I find.
Answering the previous question for me.
Yeah, answering questions. So are there any further questions from the audience?
I have a question. Yeah.
Yes, please ask it.
I'm interested about quantum subgroups. Can you go back to there was a theorem. Yeah, there. Go ahead.
Sorry, which part are you interested in?
In the quantum subgroups part, there's a theorem of Bichon and you, I think, or you. I think forward. Go forward.
Yeah, forward. Yep.
There. So it is saying that the quantum subgroups of A are all obtained by the wreath product, or just some of them in the second item. The APs are quantum subgroups. Yeah. If I'm
so the AP is you start with a quantum subgroup on your finite sort of thing, and you bulk it up into a quantum subgroup of AX, and just like this GP, and just like GP, it's isomorphic to the wreath product of itself with the P. So it iterated wreath product, I guess, if you like.
Yeah, and the question is, can you describe all quantum subgroups like this? Do they have all this property? Because
no, so we had to I mean, I don't know. I mean, this is the class of examples that I have. And sorry, my chat is in the way, but also notice that this is an A1. So I'm not even claiming for AD.
Maybe
so there's a notion of minimality for these things, these GPs. And there's a notion for minimality in the quantum setting. But from memory, we had examples that went wrong. And so it didn't look likely above A1. So it's really a quantum subgroup of symmetric group that allowed this to happen. And yeah, I don't have the details, but from memory, maybe things weren't working if you took a quantum subgroup of A2, for instance.
Yeah, okay. And another question about quantum subgroups. You say that all quantum subgroups classified by Bichon and Vanica are self-similar, or give rise to self-similar quantum groups.
Yeah, via this AP, yeah.
Yeah. And what about other examples of quantum subgroups? Because Bichon has another paper where they classify quantum subgroups. Did you study the self-similarity in this example?
No, we haven't. No, there's lots to be done. And I'm interested in looking at as many examples as possible. But like we haven't even looked at these ones that I mentioned in Bichon. So quantum subgroups of AS4. I just know that they give rise via this AP to self-similar ones, but what are they? I think there's lots to be thought about.
Yeah, thank you. It might be interesting if self-similarity is a property of some quantum subgroups, they can be obtained like this.
Yeah.
Like, very interesting.
I have one further question. Is there a groupoid that one can associate to the alphabet, so that, say, the A, so how was it, blackboard A sub X is the sister algebra of that groupoid? And what about the subgroups?
Well, I don't know. I haven't thought about that. I know that. So there's AX. So you've got these, if you want to think in the box picture, you've got all of these projections with some orthogonality and non-orthogonality going on. I don't know. Sorry, I haven't thought about that idea, and I don't know if those relations scream out some sort of groupoid, but yeah.
Okay, and one final, silly question. You mentioned an alphabet and a tree and the symmetries of the alphabet. And I expect that at some point the Kunz algebra will appear, but it wasn't mentioned. So, I expected this to show up, but it didn't. So, anyway, and
it's in most of my other talks, but yeah. Yeah, we actually in our first attempts at coming up with this self-similarity for quantum groups, we did mess around with the Kunz algebra being involved in some sort of cross product, but yeah, that's totally was the wrong idea, and yeah, it doesn't seem to appear.
Okay. Okay. So
I ask a question?
Yeah, sorry.
Yeah.
Mark,
so I guess one thing that comes up a lot in self-similar groups, the standard ones, is taking Kunz-Pimsner algebras of them. Can you do the same here? And in that case, I guess the Kunz algebras would show up if that's the case.
Well, yeah, I found it weird for a long time that we were doing like C-star algebra stuff, because that's what these compact quantum groups are. But it was very different to what I was used to in terms of associating C-star algebras to self-similar actions. So I
think that's just an extra step. So in the classic case, you take the reduced group C-star algebra of the full group C-star algebra, I guess, of the group, and then make a Kunz-Pimsner algebra by taking the alphabet as your bimodule. And I guess you could do the same thing here, where you take the self-similar quantum group as a coefficient algebra of a bimodule, and then see what happens when you put it all together.
Yeah, so there's certainly well-established notions of actions of quantum groups, compact quantum groups, which are basically coactions. So yeah, if you grabbed a self-similar quantum group and found the right thing for it to act on, like you said, some sort of bimodule or something, then
but doesn't it act on So it doesn't act on the quantum automorphisms?
Um,
I mean, it sort of acts on the
yeah.
tree, doesn't it?
Yeah, I guess it would. You could set up a coaction of that on AX.
So I think that's all you need, and then you can wonder sort of what sort of Kunz-Spindler algebra you get out of this structure, I think.
Yeah, so I don't know, is it some...
I mean, so sorry, I'm putting you on the spot because
No, well, I know I was going to say a coaction cross product, but
I think you just do the standard
a quantum coaction cross product or something.
Yeah,
I don't know.
exactly. Yeah. I think it should just work, is what I'm saying.
Okay, yeah. Well, yeah, I haven't thought through the details. Yeah.
Oh, and thanks for the talk. It was really great.
Yeah, no worries. Thanks for coming.
Okay, so I will stop the recording now.